text, Approximate Methods of Higher Analysis by Kantorovich and Krylov, contains an analytic approximation technique for boundary value problems with a homogeneous elliptic equation. I'd like to share this with you, applying it to a particular case of Laplace's equation over plane regions. Let's begin with a glimpse at the technique itself. In the notation of Kantorovich and Krylov, this would be the elliptic equation. Think of this as Laplace's equation with some boundary data. So here's what you do. You obtain an infinite set of harmonic functions, because I'm thinking that M is Laplace's operator. And in reality, you only use a handful of these functions. So these are functions that satisfy Laplace's equations, but not necessarily the boundary conditions. Well, you parameterize the boundary, evaluate each of these harmonic functions on the boundary, and call the resulting functions of the boundary parameter phi sub k. Then orthonormalize those functions, called the orthonormalized version psi sub k. Expand the boundary function, boundary data function, in a series using these psi functions. So the coefficients would be these integrals. Then use those very coefficients in a series expansion of the solution you're looking for in terms of these harmonic functions. So I ran across this in Kantorovich and Krylov and looked at their example, which they painstakingly implemented by hand calculation, because this text goes back to 1931. It was revised after the war, and there is at least one English translation that dates to the middle 60s. That's the one I have a copy of. I was amazed. I had never seen anything like this. I said, I want to implement this in Maple, and I want to see the difference in outcome and how hard it is to do it in Maple. Does Maple provide tools that were not available in these earlier days? So here's the example that Kantorovich and Krylov presented in their text. The boundary value problem was Laplace's equation on this square, minus 1 to 1 in each direction, x and y, with 1 minus x squared as the boundary data top and bottom, and 1 minus y squared as the boundary data left and right. So before getting the approximate solution, let's see if we can get an exact solution so we have something to compare to. Now, there are two quirks of Maple's pdsolve command that I'm going to be using. One is the rectangle or the square has to be in the first quadrant. I have to shift this so that the lower left corner is at the origin. The other quirk is Maple can solve the problem if there is only one non-zero edge. And so I have to solve 4 separate problems where the non-zero edge is at the bottom, right, top, and left. Then I will add those, but the problems that I have to solve have to be shifted. So here are the translations that I used. X is alpha minus 1, y is beta minus 1. Then 1 minus x squared, 1 minus y squared become 2 alpha minus alpha squared to beta minus beta squared. Here is Laplace's operator. So this is the left-hand side of Laplace's equation. And here are the 4 solutions that Maple generates for the 4 problems W1 through W4. You can take a look at the coding that's behind the cells. See, I've got hidden input. If I show that input, you can see it's pdsolve. There's the Laplace operator, and then 3 homogeneous 0 boundary conditions and 1 non-zero boundary condition. And Maple returns these 4 solutions. I have to add them. So here I've added them. Then I have to replace alpha and beta with x and y. And so I get this very large sum of terms. And I'm going to want to draw some graphs, so I'm going to pick a 10-term approximation. So it's a partial sum. And you can get that by simply replacing this infinity symbol with some number. Then you want to draw some graphs to see how well you did. This is a graph of this U10, the 10-term partial sum. And I looked on one of the bounding edges, so I graphed 1 minus x squared in green, and the solution U10 when y is 1. The fit appears to be very good. Now, Kantorovich and Krylov claim that at the origin, right, here's at 0, 0, the value of the solution, and they claim the exact value is 0.816. But this function U10 evaluates the 0.821. And I added 10 more terms and went out to 20 terms, same number. So Kantorovich and Krylov, working with pencil and paper, their hands are tied, they're handcuffed by the lack of good tools. So now let's look at the approximation technique following in Maple what Kantorovich and Krylov did with their set of tools, basically pencil and paper. I want to obtain that collection of harmonic functions. So working in the student vector calculus package, I apply the pdsolve command to the homogeneous Laplace's equation, and Maple comes back and says, here's a form for a general solution. A function, arbitrary function of y minus ix and an arbitrary function of y plus ix. So I played around with that, and I said, okay, let's take as the arbitrary function of y plus ix polynomials. So y plus ix to the n. Then I expanded it out, and I realized, okay, I should take the real and imaginary parts. So here is the real part of a bunch of y plus ix to the n. And here's the imaginary part. Now the very first polynomial that this generates is 0. And so that's what I'm doing here, is I am removing the 0 from this bunch. Then use the union command to put all of that together, and you can see what it came out to be. 1 degree, 2 degree 1 terms. This is degree 0 term. Its companion was the 0, which I drew out. Degree 1 terms, 2 degree 2 terms, 2 degree 3 terms, and so forth. And I guess this last one is a pair of degree 8 terms. The next step is Gram-Schmidt orthonormalization. How will we do that? We're going to use Maple's path in command in the vector calculus, student vector calculus packages. It will integrate along a path. It integrates a scalar along a path, and it uses arc length as the parameter. So here I define the path, collection of line segments joined at these nodes. You notice I have the 5th node is the starting point, so it completes the loop around. This is the first psi function. Path in does the integration. C stands for the syntax that it takes to tell the path int command to integrate around this polygonal path. Here I'm counting the number of elements. I think it was 17. This step right here is the Gram-Schmidt orthonormalization step, because I'm going to normalize each function after I obtain it. And Gram-Schmidt, you take a function, you subtract off the components you don't want, components along the previous orthonormal vectors, and then normalize at the end. So this loop creates a collection of psi functions. And what do they look like? Well, here you're going to have a constant, was the first one. These are the degree 1. Here are the degree 2, and so forth. Now imagine doing this by hand. Just imagine doing that by hand. The possibility for making mistakes. Kantorovich and Krylov floated coefficients and they rounded them off to 3 places. I mean, the tools we have now are just amazing in comparison to what was available. And when they did this, now the book was published in '64. I graduated from undergraduate school in '63. This is back in the days when I was a young man, and you would have to work with just a collection of primitive tools. Now we have to expand the boundary data function in terms of these psi k's. Now I'm going to define the syntax for integration along each segment of the polygonal line that makes the boundary of the square. And I'm going to apply pathInt on each segment because the function I'm integrating here changes. There's a 1 minus x squared, then there's a 1 minus y squared, then there's a 1 minus x squared, then there's a 1 minus y squared. That's why I can't use the c that I had defined earlier, because the companion function here that I'm integrating against changes. So this gives me a sequence of numbers. That sequence is the name A. So put square brackets, makes it a list. What do I have? 3 non-zero terms. Now these zeros in the middle, Kantorovich and Krylov got rid of early on in their discussion by recognizing that there's a lot of symmetry in this problem, and they use that symmetry to rule out a whole bunch of these psi functions before they ever got started. And they would have to do that because they just can't throw something at the computer and say, okay, do the calculations. And so here are 3 non-zero coefficients, and I will form 2 approximations according to this technique. One with 2 terms, right, these 2 terms, and one with these 3 non-zero terms. This is what the 2-term approximation looks like using Maple, and this is what the 3-term approximation looks like using Maple. And finally, we want to test the accuracy of the approximation. I mean, anything is an approximation. It's just the question of how accurate is anything that you write down, right? So here are some experiments to see how accurate the approximations are. So here is the 2-term approximation. Remember, this is the Maple approximation. I graph 1 minus x squared in black, and in red is the 2-term approximation. Close, not perfect. This is the 3-term approximation. Well, you can't see a difference between them visually, graphically. How else can we compare these? You could draw the solution surface. So the solution surface, exactly using our U10, that's drawn in green, and the 2-term approximation drawn in red. And here is the 3-term approximation drawn in red. And they're very close. But how close? Let's see if we can determine analytically or some other way of just how close is close. So here I'm graphing the difference, the absolute value of the difference between our exact solution and the 2-term approximation. And you see the amount by which these corners spike up, 0.04. If I use the 3-term approximation, it's 0.01. So presumably if you add more terms, you can reduce the spikes in these corners even more. Now, another approach is to look for the max over the domain. Well, the max over the domain, if you hunt around, 0.459, which is consistent with this figure here. And if you look at the 3-term approximation, then it's 0.109, which is consistent with this figure here. And finally, this is what Kantorovich and Krylov actually display in their text as their approximating sum. This is how they wrote it. You can see they used a combination of floats and exact values. If you test this at the origin, you get 0.814. And they say that the exact value should be 0.816. Well, we found that the exact value is more like 0.821. Now let's look at these two approximations that we have computed according to the recipe that Kantorovich and Krylov wish they could have followed if they had the right set of tools. They turn out to be exactly and 0.821 and exactly and 0.821. So the evidence using Maple is even better than the evidence that Kantorovich and Krylov were able to generate using the suite of tools that were available to them at the time. Well, flush with the thrill of having implemented the solution or reproduced the solution that was in the text, looked around and said, okay, let's try some other domains. Let's see what we can accomplish. So you can see these three problems are ones that I devised. I tried this technique over an ellipse, over a triangle, and over a region bounded by two arcs. First of all, for the ellipse, what is the boundary value problem? Well, here is the bounding ellipse. It goes this way. All right, it's -2 to 2 this way and -1 to 1 this way. I started with a harmonic function. I rummaged around, found a harmonic function, and for the boundary data, I simply evaluated this function on the boundary of the ellipse. So here's my boundary data. Now what does it look like? This is what the solution surface, this is exact because I'm starting with the exact function. So this is what the boundary function looks like. Where did I get this function from? Well, I took this linear fractional transformation, took the imaginary part, played around with it, ended up with this thing, said this is what I'll use for my exact problem, exact solution. So we have the boundary value problem. How do we get started? Well, I built into the worksheet here the way I obtained my solution, the exact solution, little v, is the imaginary part of this function. Then I generated, and this is the same technique I used for the Kantorovich and Krylov example, the psi functions. I defined a path that would be known to Maple's path in command, knows that it's an ellipse. Next step is the Gram-Schmidt orthonormalization process. And essentially, the same code works here. Define the first psi function, then apply Gram-Schmidt techniques where you subtract off the components you don't want, and then normalize. So I generated this sequence of psi functions. And you look at this and you say, well, wait a minute, now these are all floating point coefficients. Where did the integration switch to decimals, numbers? It's right here. This decimal point right here, included in the definition of the path, tells the path in command that it is okay to go ahead with numeric integration. And when you look at what these integrals are, you end up with elliptic integrals because you're going around the boundary of an ellipse. So that's why these things are floats and had to be done as floats. Next step, expand the boundary function in terms of these psi k functions. So you need coefficients, and they can be obtained via the path in command, where you are integrating the exact function against the psi k's. Now you notice I did not have to change this to the boundary function, because on the path, Maple's path int does the evaluation of the function of two variables appropriately. And again, this is an illustration of the power of the new suite of tools available to today's worker. Okay, so one gets a list of these coefficients. You notice there are a couple of 0 ones, and then there's some 0 ones interspersed between. So the approximate solution now will be uppercase V. It's just sum across the psi functions using these coefficients that we've just calculated. The ones that are 0, fine, just let Maple take care of it. And this is what the approximating solution looks like. And now again, we want to see just how good a job does this approximation do. Let's test the accuracy in some of the techniques that we used earlier. Okay, so in green, we graph the exact solution. And in red, we graph the approximate solution. And they're intertwined and lying on top of each other. This is a graph of the absolute value of the difference. The worst difference is somewhere up around 5/1000ths. Let's look on an edge or on the boundary. This is the absolute value of the difference between the exact and the approximate, looking at it on the boundary. So right at pi seem to have the worst error, and it's on the order of 0.07. If you look at the graphs of the exact and approximate along the boundary, they look to be right on top of each other, because a graph is not going to pick out the difference as small as 7/1000ths. So here's numerically. Let's get the inf norm of difference in absolute values working along the boundary. And it's a little bit more than 7/1000ths, consistent with this figure. I think this is an amazing approximation technique. I've never seen this in any of the textbooks that I've read over the course of my career, and was amazed at the performance of this technique and how easy it is to implement it in Maple. Well, how about on a triangle? What would it be like to do this over a triangle? Okay, same exact solution, and then just evaluate it on the 3 edges of a triangle. What is my triangle? Well, I took this as the triangle. I thought making one of the edges coincide with coordinate axis would make things a little simpler. I'm not so sure about that. But anyway, here is the triangle I picked. Here are its edges. These are the equations of its edges, and these are the values of this exact function on these 3 edges. And here is a graph of the solution surface over that triangle. Then I drew the edge values over each edge of the triangle. Later I'll superimpose on this the graphs of the approximate function, approximating function on the edges. And here again is a reminder of how I obtained this exact problem. Same as I obtained for the ellipse. Okay, the problem solution begins. As we did earlier, I've rebuilt, so I have a restart. I've rebuilt the exact solution V. I've rebuilt the collection of psi functions, and I think I only went out to 6 rather than 8, so I use fewer functions. I define a path that the path in command will understand. It's the line segments going around the nodes or vertices of the triangle. You have to put the first one as the last one to close the loop. Next is the Gram-Schmidt orthonormalization of the psi functions. Same structure. Define a first psi. This is just simply counting up the number of functions. This is the Gram-Schmidt step, where you subtract off the pieces you don't want, the components along previous vectors. And here is the normalization step. And you'll notice that here, because there's floats involved, right here, this is where the floats kick in. This is a rounding function, and then a simplify. So what do these things look like when we're done? This is the collection of psi functions, right? And the coefficients are floating point numbers. Imagine doing that by hand with a pencil and paper. The next step is to expand the boundary functions in terms of these psi k's. Here is the path int command. Notice that you can use the path definition and again the exact solution function, because the path in command will evaluate it on the boundary, so you don't have to go through the trouble of expressing each boundary condition separately. So you get a list of coefficients. This is what they look like. They will be floating point numbers, and I don't think that any of them turned out to be 0. This is the approximating solution. It's the sum using these coefficients of these psi functions, and this is what it looks like if you write down that approximation. Now, of course, we want to test the accuracy of this approximation. And here we have drawn again in green the exact solution, that's little v, and the approximating solution in red, that's big V. If we look at the graph, the absolute value of the difference, according to this graph, is the worst difference is on the order of 5/1000ths. This is what it looks like if you graph the approximate solution against the exact solution strictly on the boundary. This is a set of graphs of the absolute value of the difference between the exact and approximate looking just on the boundary. You can see the worst error seems to be on the order of 7/1000ths. This is less than that. This is on the order of 7/1000ths. So let's look at the inf norm of the absolute value of the difference on each of the three edges. So the worst error, max error, is on the order of 6, maybe 7/1000ths, maybe 7/1000ths. That's consistent with these two graphs. Pretty good approximation analytically. So by this point in my investigations, I was feeling pretty good about things, and I said, okay, we need one more region, very, very different from these two, a region bounded by two disparate arcs, one of my favorite regions. And you'll see a graph of the region here. I'm using the same exact function. This is the region I picked, bounded by a piece of a sine curve, piece of a cosine curve. I use something like this in lots of examples that I've concocted over the years. Pi upon 4 is the smallest x, 5 pi upon 4 the largest x. Two separate arcs. This is what the exact solution looks like over that region. Again, I've used the same v that I've used 3 times already. To begin then, we do a restart. We recreate the exact solution v. We generate a list of psi functions, and here again I've only gone out to 6. The first one has a 0 in it, so I take that out. So here are the psi functions. Then I define the arcs that bound the region. These are defined parametrically via the path option that the path in command will then understand. Now, the Gram-Schmidt orthonormalization process. Well, it turns out that because you have these two branches, two pieces to the path, two arcs in the path, you can't just simply throw this integration process at the path in command, because on one you're integrating along one arc, then you're integrating along the other arc, and you'd be writing path int across the screen. So I wrote a little procedure: integrate on the contour. It generates the sum of the two path integrals, one on the cosine branch and one on the sine branch. So instead of having to write out all of this every time I wanted to do an integral, I could just simply write down integrate on contour, give it the function that I'm integrating. Right, this is the function that I'm integrating, and let Maple do the rest. And I will point out one other curious thing. Initially, I had defined the path to be counterclockwise. So I started out, if you think about the cosine branch, that's not the bottom. The bottom one is the cosine branch. So there I went from pi upon 4 to 5 pi upon 4. And then on the upper branch, the sine branch, I went from 5 pi upon 4 back to pi upon 4. That didn't work because Maple's path in command, it takes care of the direction. So it wasn't until I realized that I just should put both of these arcs from pi upon 4 to 5 pi upon 4 that things would work out. So here is the Gram-Schmidt process using this integrate on contour command. So the integrate on contour command takes the place of path int over two pieces, and everything else is the same. And here is an eval f. I'm floating. This is a rounding and a simplify, and these are the resulting psi functions. They're extremely messy. I could not imagine doing any of this by hand. It's just beyond belief. But with the tools of Maple, it's just a snap. Now, expanding the boundary value function in terms of the psi k's gives the coefficients a that you need, and the process is the same, except that integrate on contour replaces the appearance of path int, but built into the IOC is the path int command, so I get back a list of coefficients which I use in this sum against the psi functions, and I get this approximate solution V. This is what that approximate solution looks like. And finally, we want to test the accuracy of this approximation. So this is a graph of the exact solution in green and the approximate solution in red. I mean, the red pixels are embedded in that green surface. This is a graph of the absolute value of the difference. Look at the magnitude of the worst spike here. It's on the order of 3, what is that? This is tenths, hundreds, thousands, 10,000s, 300,000s. If you look on the boundary, simply on each arc on the boundary, you can't see any difference between them. If you look at the absolute value of the difference on each arc, so that you get a sense of the magnitude of the error, here it's you got 4 zeros here, you have 4 zeros here, very, very small error. And then using the infnorm command, you find out that the worst error is on the order of 4 zeros here, 32. Amazing accuracy for a process that can be implemented in Maple with, I think, less tedium than it would be to set up a numeric solution. Because remember, Maple does not have a numeric solver for elliptic problems.